You've looked in a mirror every day of your life. It's something so routine, you don't think twice about it. You check your face in the morning, make sure your hair's in place, and you're good to go. But have you ever stopped to think about what's actually happening when you look at your reflection? You've heard the phrase, light bounces off a mirror, and you've probably accepted that explanation. It seems simple enough, right? Light hits the mirror, bounces back, and you see your face. Obvious. Done. But what does bounce mean in this context? When I say a ball bounces off a wall, I can picture it. The ball hits, compresses, and springs back. There's a clear mechanism at play. The ball compresses a little, stores some energy, and then releases it, bouncing off the wall. That's something you can grasp. But light doesn't have mass or a surface. So when light hits a mirror, what happens then? It doesn't compress. It doesn't spring. It doesn't do any of the things a ball does when it bounces. So what exactly is going on when light bounces? Here's the problem. When you look at a mirror, you see a reflection. But the process behind that reflection is anything but simple. Mirrors are not just reflecting light. They're doing something far stranger. Let's think deeper. A mirror, at the atomic level, isn't solid in the way you might imagine. It's made up of atoms, just like everything else. Atoms are mostly empty space, with electrons and nuclei separated by vast distances. There's no solid surface for anything to bounce off. So how does light interact with this atomic structure? You see, we've all been conditioned to think of light as something that simply bounces back from a surface. But if you break it down to its core, what's really happening when light encounters a mirror isn't bouncing. It's something far more complex, and it's tied to quantum mechanics, probability waves, and the fundamental nature of light itself. What happens in that moment when photons, those tiny particles of light, hit the surface of the mirror is nothing short of strange. So, let's dive in and explore what's actually going on. It's easy to assume that mirrors work just like everyday objects we've come to understand. When light reflects, we picture it like a ball bouncing off a wall. But that analogy doesn't do justice to the reality. In fact, it hides a much deeper mystery. To truly understand how mirrors work, we have to step into the quantum realm, where things behave in ways that completely defy our usual expectations. When light reflects off a mirror, it's not just bouncing back in the way you might think. The process involves quantum phenomena, something that breaks the rules of classical mechanics. Light, when it hits a mirror, doesn't bounce in the way a ball does. The photon is absorbed by the mirror's surface. It doesn't compress or recoil like a ball. Instead, it's annihilated. The photon is gone. What happens next is where the real magic occurs. The mirror creates a new photon. The original photon is gone, absorbed by the mirror, and the mirror then emits a brand new photon, exactly like the original, but traveling in a different direction. This isn't a simple bounce. It's the destruction of one photon and the creation of another, identical but reborn. This is where we need to stop and think. What's really going on here? It's not just a matter of light bouncing off something. It's a process of absorption and re-emission, a process that involves the mirror's atomic structure. The photons that reach the mirror are absorbed by free electrons in the metal, and those electrons oscillate in response, creating new photons that are emitted back in the direction of your eyes. And yet, we still say that light bounces. But the reality is far stranger than that. We're not just watching light reflect. We're witnessing the destruction of light and the birth of new light. This act of re-emission creates the illusion of a reflection, but the photon you see in the mirror is not the same photon that originally hit it. It's a recreated photon that has been born from the interaction between light and the mirror's atoms. Now, let's look at the atomic structure of the mirror itself. A mirror is typically coated with metal, like aluminum or silver, which is arranged in crystalline layers. These metals have a special property. Their outer electrons are not bound to specific atoms. Instead, they form what's known as an electron sea, where the electrons are free to move across the entire material. This is why metals are good conductors of electricity, and it also plays a crucial role in how mirrors reflect light. When a photon, the particle of light, hits the mirror's surface, it doesn't bounce off in a traditional sense. The photon's electromagnetic field starts to interact with the free electrons in the metal. The electrons, which are charged, respond to this field. As the photon's field pushes on these electrons, they start oscillating in sync with the incoming light. Now here's the key part. When these electrons oscillate, they generate their own electromagnetic radiation. This process is governed by one of the fundamental rules of electromagnetism. When a charged particle accelerates, it emits electromagnetic waves. In simpler terms, the oscillating electrons create new photons. These new photons have the same frequency, the same energy, but they're emitted in a different direction. This new photon is essentially the reflected light you see. The original photon has been absorbed, and a brand new one has been created, traveling in the direction that forms the image in your eyes. The reflection you see isn't a bounce, it's a transformation, an interaction between the incoming photon and the electrons in the mirror that results in the emission of a new photon. So, when you look into a mirror, what you're actually seeing is the result of countless individual interactions between photons and electrons. The image you see is not the same light that left your face moments ago. It's a recreation of that light, generated by the electrons in the mirror. The mirror doesn't just reflect light, it absorbs it, alters it, and then emits a new photon. And this isn't just a simple reflection. It's a process that happens at the atomic level, involving the creation and annihilation of photons. But why is this important? Why does it matter that light isn't actually bouncing off a surface? The reason is that it gives us a much deeper understanding of light and the nature of mirrors. It challenges the common misconception that mirrors simply reflect light in a mechanical way. The act of reflection is far more complex, involving quantum mechanics, the absorption and re-emission of photons, and a deep connection between light and matter that most people don't realize. Now, you might be wondering, if all materials absorb and emit photons, why isn't everything a mirror? Why do some surfaces, like a polished metal, reflect light perfectly, while others, like a white wall or paper, just scatter it? The answer lies in the structure of the surface. Materials like mirrors have a very smooth, well-organized atomic structure. The metal's crystalline layers are arranged in an orderly fashion, which allows the electrons to oscillate in sync, creating new photons that are emitted in a uniform direction. This coordination ensures that the light reflects in a way that preserves the spatial relationship of the image, and that's why you can see yourself clearly in a mirror. On the other hand, materials like walls or paper have a disordered atomic structure. When light hits these surfaces, the photons are absorbed and re-emitted. But because the atoms are arranged in a chaotic way, the new photons are emitted in random directions. This results in scattered light, and because the photons from different parts of your body are emitted in different directions, the image you see is lost. Instead of a reflection, all you get is a bright surface with no clear image. The difference between a mirror and a wall comes down to the level of organization in the material. When you polish a rough surface, you're not changing its chemistry, you're organizing the atoms. The smoothness of the mirror's surface allows for a high degree of coordination in how photons are re-emitted. This organization turns chaotic light scattering into a clear reflection. A rough surface, on the other hand, destroys the coherence of the reflected photons, resulting in a diffuse, unrecognizable light pattern. So, to recap, when light hits a mirror, it isn't just bouncing off a solid surface. The photon is absorbed by the electrons in the metal, which then re-emit a new photon in the direction of your eyes, creating the reflection. This process is quantum in nature and involves the destruction and creation of photons. A mirror doesn't reflect light in the traditional sense. It creates a new photon that carries the same energy and frequency but travels in a new direction. And this brings us to the next question. If the photon is created anew each time, how do we even know that the reflection is accurate? The answer lies in the precision of the quantum interactions. Every time light hits a mirror, the photons are emitted with extreme precision. This is why you can see yourself clearly in a mirror. It's not just a random re-emission of light, but a calculated, coordinated process that preserves the information and produces a perfect replica of the original image. Now, let's delve deeper into the quantum mechanics behind this. Up until now, we've been talking about how the mirror interacts with light in a classical sense. However, at the quantum level, things get much stranger. And this is where your understanding of light and matter is really put to the test. We already know that light behaves both as a wave and as a particle. This duality is a key feature of quantum mechanics, and it's one of the most mind-bending aspects of our universe. When you think of light, you likely picture it as a stream of photons, small packets of energy that travel in waves. But light isn't just some simple wave that moves in one direction. According to quantum mechanics, each photon doesn't just follow a single path to the mirror. It takes every possible path simultaneously. Imagine you're standing in front of a mirror, and light is traveling from your face to the mirror and then back to your eyes. In classical terms, you would think of the photon traveling in a straight line from point A to point B. However, in the quantum world, things are much more complicated. The photon doesn't just travel in one straight line. It simultaneously travels all possible paths, bending left, right, up, down, and everything in between. Each of these possible paths is part of a mathematical probability wave that tells us where the photon is most likely to be. This is what quantum mechanics calls superposition. The photon's path is a superposition of all possible paths it could take, and this is a crucial part of the process that leads to the reflection in the mirror. When you look at your reflection, the photon's superposition collapses, and it manifests as a single path, the one that aligns with the classical trajectory of the light bouncing off the mirror. But before it collapses, the photon has already experienced all of these different potential paths. This isn't just an approximation or a metaphor. It's the true nature of quantum mechanics. The most mind-boggling part of this is that the photon doesn't decide on a single path until it's observed. Until that moment, the photon exists as a cloud of possibilities, a probability wave that can't be pinned down. When it interacts with the mirror, it's not simply bouncing off a surface. It's undergoing a quantum process where all possible paths are taken into account. The act of the photon being detected, whether it's in your eye or the mirror, causes the superposition to collapse into one definite path, and that's the reflection you see. But this doesn't just apply to light and mirrors. This principle of quantum superposition extends to all particles, and it's at the heart of many of the strange phenomena that quantum mechanics describes. The idea that particles don't have definite positions or paths until they're measured goes against everything our classical intuition tells us about the world. We're used to thinking of objects as having specific locations and trajectories, but at the quantum level, things aren't that simple. A photon, or an electron, can exist in a multitude of states at once. It's only when we measure or observe it that we see a single outcome. The rest of the possibilities are no longer accessible. This is what makes the behavior of light in mirrors so fascinating. Every time you look into a mirror, you're witnessing a quantum event in action. The photons coming from your face, reflecting off the mirror, and returning to your eyes are not just following a simple, deterministic path. They're taking every possible path simultaneously until they collapse into the reflection you see. You may be wondering, how does this affect our everyday understanding of reflections? Why does all of this weirdness matter in practical terms? The answer is that it shows us just how far our intuitive understanding of the world is from the true nature of reality. The fact that light can behave as both a wave and a particle, that it can take multiple paths at once, and that its behavior is influenced by quantum mechanics completely changes how we think about reflection. Now let's take it even further. A fascinating aspect of quantum mechanics is that even though we can't directly observe all of the paths that the photon takes, we can calculate the probabilities of each of them. When you look in a mirror, the photon you see is just one of many possible outcomes. In essence, what you're witnessing is the result of a quantum calculation that takes into account all of the possible paths the photon could have taken. This calculation, in the form of probability amplitudes, gives us the correct result, the reflection you see in the mirror. But wait, there's still more to this picture. If you were to try and predict which photon would be the one to reflect off the mirror and which would transmit through glass, you'd encounter something fundamentally unpredictable. Even with all the precision that quantum mechanics offers, the exact path a photon takes is still subject to chance. It's as though the universe rolls a weighted die for every photon that interacts with a surface. Sometimes the photon reflects, and sometimes it doesn't. The outcome is determined by probability, not by any hidden variables. This is a core concept in quantum mechanics. The idea that at the most fundamental level, the universe is not deterministic. Things don't always follow predictable paths. Instead, they follow probabilities. So when you see a reflection in the mirror, you're witnessing a result of an inherently random process, one that is governed by the laws of quantum mechanics. The light you see in your reflection isn't a certain path that the photon has taken. It's the result of a calculation involving all possible paths. And yet, despite this randomness, everything works out in the end. The reflection is clear, the image is intact, and this chaotic quantum process gives rise to the familiar, predictable world we see around us. This is the beauty of quantum mechanics. It provides a framework for understanding how things work at the smallest scales, even when they seem utterly mysterious to us. What does this mean for you, standing in front of a mirror, looking at your reflection? It means that you are witnessing the interaction between light and matter in a way that's far stranger than you ever imagined. Every time you look into a mirror, you're participating in a quantum process that defies classical explanation. You're seeing light interact with electrons in ways that don't make sense on a human scale, but work perfectly when viewed through the lens of quantum mechanics. Now, you might be wondering why any of this matters. Why should we care about these mind-bending quantum principles when all we're trying to do is see our reflection in the mirror? The answer lies in how this quantum understanding reveals something profound about our perception of reality itself. When you look in a mirror, you're not just seeing light bounce off a surface. You're witnessing the very process of how the universe works at its deepest level. And that's the kind of thing that should change the way you view the world. Think about this. You've always understood that you look at your reflection because light bounces back to your eyes. But what you're actually witnessing is a deep quantum interaction where photons are annihilated and recreated, where probability waves play out, and where things that seem like simple events, like seeing your own face, are governed by complex unseen forces. The mirror, in its seemingly mundane function, is actually revealing the true nature of reality. And this extends beyond just reflections. The same principles that govern how photons interact with mirrors are at play in everything around you. The way light bends, how particles behave, and even the technology we rely on, like quantum computers or medical imaging, all stem from these quantum principles. Our entire understanding of physics, from the smallest particles to the largest galaxies, is built on these ideas. The mirror, in this sense, is just a reminder of how strange the world is at its core. When you look at the glass in front of you, you're not just seeing a reflection of yourself. You're seeing a quantum dance happening right in front of your eyes. Light isn't just bouncing. It's being destroyed and created, following paths that aren't so obvious but work perfectly every time. The most astonishing thing is that this isn't just some theoretical exercise. These ideas are behind every single part of our modern world. Quantum mechanics may seem like a distant, abstract concept, but it shapes everything. Whether it's the sun shining above you, the photosynthesis in plants, or even the smartphone in your pocket, all of it ties back to the quantum nature of light and matter. So, the next time you stand in front of a mirror, don't just look at it as a simple reflection. See it for what it is, a quantum miracle, one that happens every second and explains the very nature of our universe. It's not magic, it's physics. The mirror is your window into a deeper, stranger reality, one that we're only beginning to fully understand. If you want more of this to keep exploring the true nature of our world, hit that subscribe button and keep discovering what's really going on beneath the surface of reality.